States of matter, so a few basic things that we study right from class 5 or 6, and but we're gonna keep them over here since we're gonna extend them to a much higher advanced set of details. ठीक है, गैसेस की कोई फिक्स शेप या वॉल्यूम नहीं होता. ठीक है, इनकी शेप कंटेनर की होती है, जबकि वॉल्यूम के बारे में हम ये कहते हैं दे ट्राई टू occupy all available space. So they fuse, they diffuse, they go with many phenomena, they expand to get to cover as much space as they can. गैस पार्टिकल्स फार अपार्ट होते हैं, दैट्स देयरफॉर गैस को कंप्रेस किया जा सकता है. ये रेंडमली अरेंज्ड होते हैं और रेंडमली मूव करते हैं फ्रीली फ्रॉम वन प्लेस टू अनदर इन ऑल डायरेक्शंस. रैंडम मोशंस इंक्लूड्स मोशन इन स्ट्रेट लाइंस, जिसे हम लीनियर भी कहते हैं, और इस बुक में हम उसके लिए ट्रांसलेशनल का वर्ड भी यूज करेंगे. ठीक है, इट कैन बी अ सर्कुलर मोशन, इट कैन बी समटाइम्स वाइब्रेटरी, बट दो दोज कंडीशंस आर वेरी लेस. ठीक है, इट कैन बी स्लाइटली रोटरी, ये अपने गिर्द भी स्पिन कर सकता है. सो हेंस द फ्रेज रैंडम मोशन. लिक्विड्स टेक द शेप ऑफ कंटेनर दे ऑक्यूपाई, इनका वॉल्यूम फिक्स्ड होता है क्योंकि लिक्विड अपना लेवल मेंटेन करते हैं. ठीक है, लिक्विड पार्टिकल्स समवट क्लोज होते हैं टुगेदर. लिक्विड का फिक्स वॉल्यूम होता है, स्लाइटली कंप्रेस किए जा सकते हैं, वो भी फ्यू लिक्विड्स. ऑल लिक्विड्स के लिए हम ये बात नहीं करते हैं. ठीक है, उसने लिक्विड पार्टिकल्स का वर्ड इसलिए यूज किया क्योंकि पार्टिकल्स को हम एक जेनेरिक टर्म के तौर पे यूज करते हैं. वी डू नॉट स्पेसिफाई ऑल कोर्स सिचुएशन. ठीक है, सबके लिए नहीं करते हम. For mostly arranged randomly, they have limited movement from place to place in all directions. We commonly use the phrases slide past one another, move past one another. Slide past one another is a phrase that we most commonly use as a childish phrase, but this childish phrase has a pretty good impact when it comes to flow. तो हम फिर liquids को fluids में gases के साथ शामिल भी कर सकते हैं, and we can safely say that liquids flow, but unlike gases, their flow is slower. All right, as compared to gases. Solids fixed shape hota hai, fixed volume hota hai. The particles are touching one another. They actually cannot move them from their main position, so they cannot be compressed and they can only vibrate. ठीक है, इनकी regular arrangement होती है. और solids में फिर हम आके जब further specify करते हैं तो basically lattices भी solids के लिए ही exist करते हैं, since वो इतनी networked अच्छी arrangement होती है कि वो उस तरह से हो सके. ठीक, उसके बाद स्टेट ऑफ सब्सटेंस रूम टेम्परेचर प्रेशर पे डिपेंड करता है, स्ट्रक्चर पर, बॉन्डिंग पर, इंटरमोलिकुलर फोर्सेस पर. ठीक है, 4 टाइप्स ऑफ स्ट्रक्चर हमने एलिमेंट्स और कंपाउंड्स के डिस्कस किए हैं. सिंपल मॉलिक्यूलर सिंपल एटॉमिक स्ट्रक्चर थे, जो हमारे पास कार्बन डाइऑक्साइड, आर्गन, कुछ बेसिक लिक्विड्स, सॉलिड्स, गैसेस में एग्जिस्ट करते थे. सॉलिड्स की एग्जांपल रिलेटिवली कम थी, गैसेस की एग्जांपल्स काफी ज्यादा हैं. आयनिक में हमारे पास जाइंट लैटिसेस हैं और तकरीबन तमाम आयनिक कंपाउंड जैसे ही हैं. मेटालिक में भी हमारे पास जाइंट मेटालिक हैं. ठीक है, मॉलिक्यूलर में जाइंट मॉलिक्यूलर हैं, ये यूजुअली कोवलेंटली बॉन्डेड हैं. डायमंड, ग्रेफाइट, सिलिकॉन, पेरोक्साइड इसकी एग्जांपल्स हैं. ठीक है, रिमेंबर अगर आपने 2 एलिमेंट्स यूज कर लिए इसमें तो वो कंपाउंड हो जाएगा, सिंगल एलिमेंट है तो वो एलिमेंटल फॉर्म ही रहेगी, which means diamond and graphite are actual elemental examples of giant molecular structures. ठीक है, तो उसने इसके आगे जाइंट मॉलिक्यूलर के आगे कंपाउंड्स या लैटिस या इस तरह के वर्ड्स इसलिए यूज नहीं किए क्योंकि हर एक के लिए हम डिफरेंट वर्ड्स या कॉम्बिनेशन ऑफ वर्ड्स यूज कर सकते हैं. सो दे ट्राई टू बी एज सेफ एज पॉसिबल विद देयर राइटिंग, एंड आई आस्क माय स्टूडेंट्स टू नोट दिस पॉइंट and keep this point as a writing strategy for their answers in the paper. ठीक है, अगर बुक ये कोशिश कर सकती है कि वो सेफ प्ले करे और राइटिंग में वर्ड्स को प्रॉपरली क्लेवरली चूज करे ताकि उसे पकड़ा ना जा सके, गलत ना किया जा सके, सो यू कैन देन डू द सेम. ठीक है, जब तक तो आप ओ लेवल में थे दिस वाज इजी सिंस दे कॉल इट लीनियंट एंड दे वर एक्चुअली वेरी लीनियंट विद यू when awarding marks, so they ignore most of the stuff and reject the few to cut their marks at a very few points. When it comes to advanced level, you already know you are an adult, you have already taken the major decision about your career in life, and of course, you can handle stuff like this. You can get to a level of sophistication while writing, so you should get to one. Okay? Since they are presuming you can get to one, so you should achieve it. तो ये बात जहन में रखनी है. सेफर्ड्स भी मैं पहले डिस्कस कर चुका हूँ, एक आधी मरतबा मैं बाद में भी दोबारा करूंगा. स्पेसिफिकली जब हम पेपर सॉल्व करेंगे तब भी डिस्कस करूंगा. And I am trying to point it over here, and I'll keep pointing the same thing over and over in the book So if you're taking the words out of the book, you should also know how or which words to take. Okay? It's not O levels or it's not IGCSE and that you'll take entire sentences out of it and just throw them in the paper to get your marks in advanced levels. I hope I make my point clear, right?
Yes.
Good. Moving on. Simple atomic structures, no noble gases में मिलते हैं उनकी similar physical properties होती हैं to simple molecular gases. Although noble gases isolated atoms होते हैं, लेकिन हम उन्हें molecular structures के तौर पर ही consider करते हैं, and they are probably the only isolated atoms which are considered as molecules. When we call them molecules, there is a term that we have been using, and you might remember that that was monoatomic molecules, the only molecules which are based on single atoms. Mono means one, atomic stands for atom. So this means their structure is composed of a single isolated atom, hence this the word. All right. So since they are far away from one another, तो one atom की बजाय isolated atom एक ज़्यादा अच्छी explanatory phrase है. Again, a good word choice. The gaseous state. Let's discuss all the states one by one in details. We did that back in the O levels book, but this time there is going to be an advanced step. So what we're going to do is that we're going to start with kinetic theory of gases. Okay? Kinetic theory of gases is like a major upgrade to the discussion or to the explanation of solid state. But unlike any theory, this theory also had its limitations, or what we can say, a little bit of mistakes that had few areas of improvement, which were later improved, and since a few of the exemptions were not correct. So what we're going to do is that we're going to go with this theory and we're going to also explain the parts that required correction and what the correction was. All right. So let's get started. Let's make sure that we understand all the points one by one. The idea is that molecules in a gas in a constant movement is known as kinetic theory of gases. This theory makes certain assumptions. Number one, gas molecules move rapidly and randomly. I've already explained that. Moving on to number two, the distance between the gas molecules is much greater than the diameter of the molecule, so the volume of the molecules is negligible. Let's make an example to make understand what they're tending to say. Now, in case of molecules, let's say this is a molecule and that is its diameter. The other gas molecule, which is generically considered around the world, is supposed to be present 300 of these diameters away for our common atmosphere. So this means for this molecule and this molecule, they are actually far apart. If you stand 300 people between two people at either ends, they are actually be far apart from one another. So if we talk about combining these molecules, volume of molecules, this is a specific term and it has a specific meaning. So let's explain this term in a diagrammatic form, right? So let's say you have a box and you have a certain number of molecules that are randomly moving in that box. Let's say I've drawn 6 molecules. This is the volume of the box. The volume of the molecules is if all the molecules can be brought together and put as closer as possible in the same container. So this actually size would be negligible as compared to this one. It would hardly had any volume, since this would be 0.000 something of the overall volume. That's why we are saying this. Do you understand what the phrase volume of the molecules mean now?
Yes, sir.
As closer as possible. It doesn't necessarily means they would be touching one another.
Okay.
Okay. Number three, there are no intermolecular forces of attraction or repulsion between the molecules. This one and this one are something that we're going to find a little bit of contradictory, and we are going to make some improvements in these points. Okay, so far we're going to go with these points as they are written over here, and when it will come to the point where we need to correct them, we'll correct them, and we'll correct them with respect to certain set of scenarios. So far, let's go with the scenario that's in front of us. Number four, all collisions between particles are elastic. When I say that, I would really like to take help with the help of diagrams, and I'd like to take some help from physics. Now, I hope from physics you understand that the collisions are considered to be of two types: elastic collision and inelastic collision. Do you remember
Yes, sir.
that from physics, or do I need to explain the certain
Yes.
set of rules that we passed for it? So,
No, I think I
what
know.
is the basic difference between elastic and inelastic collision?
In elastic, the sum of kinetic energy remains before and after collision remains the same in elastic collision.
That is
Whereas
elastic, or the opposite of elastic, inelastic.
no, that's elastic, where the sum of kinetic energy before and
Right,
after
right.
collision is the same.
So you were using the word in as a preposition and it wasn't connected to the word elastic. All right, understandable. Good, good. So elastic means when two particles collide with one another, energy is completely exchanged from one particle to another. So much so this becomes the energy of this one, this becomes the exact energy of the other one. When we talk about inelastic collisions, which most of the cases are in real life, the energy is not completely exchanged. Some part of energy goes to this one and some part of energy goes to this one, and some of the energy is lost in other forms of energy. For example, if we try to strike both the palms of our hand, which is commonly known as clapping, much of the energy is released in the form of sound energy, heat energy. So the energy is not completely converted or conveyed from one side to another or vice versa. So, though this is not a very good example of collisions between particles, but this can help you understand that how the energy is lost and how the lost energy is usually converted to other forms of energy. When I give this example, students usually come up with the point that we do understand that energy is converted into sound energy and hence the word clap. Where is the part where heat energy is concerned? So if you clap for a little while, we usually clap for 5 to 10 seconds, even if we clap for a longer duration of time. But if you clap for a little longer duration than that, like 30 seconds or maybe a minute, you'd see your hands would start getting red and actually would start getting hot as well. So heat energy is there, but we usually definitely get to know it or that this is the lost energy part since we don't do it for a longer duration of time. And in the cases we're about to consider now for an kinetic to molecule theory of gases, we will consider some scenarios that we are going to consider for a little bit of longer duration of time. So keep that in mind for maybe a factor that is not a conclusive factor for a smaller period of time, but may actually be a very important one if we're going for a longer duration of time. Keep that point in mind, and I'm going to use that point a few pages later to explain something as a part of this course. All right?
Yes, sir.
Moving on. Moving on. The last point, the temperature of gas is related to the average kinetic energy of the molecules. I'd like to explain it as a simple, directly proportional relationship since when we're going to increase the temperature, the kinetic energy, average kinetic energy, not just the kinetic energy, the average kinetic energy of the molecules would increase too. Why the average kinetic energy? I'll explain the phase a little later on in this chapter, since this also requires a set of diagrams to explain it. Okay, so a theoretical gas that fits this description is known as an ideal gas. In reality, the gases you're learning about, the gases present on this planet, are not ideal gases. They're all real gases since they do not behave ideally. So the gases we are going to deal with may not show one or more than one of these points in the way they are written over here. Noble gases with small atoms such as helium and neon may come a little bit closer to the ideal gas behavior. This is because their intermolecular forces are so small. So right here, we understand that this point is going to be a problem when we're going to talk about real gases, since this would be the most deviating point when we're going to talk about the real gases. I hope the hint has been pretty clear, right?
Yes, sir.
Good. Moving on. Ideal gases have zero particle volume and no intermolecular forces of attraction. And that's the both points that we're going to change for real gases. So the volume that ideal gas occupies depends upon its pressure. We measure the pressure in pascals, right? Previously, we have been using atmospheric pressure. Remember, 1 atm is like 101,325 pascals. What we commonly do is that we call it 1 into 10 raised to power 5 or 100 kilopascal. So these are the kind of conversion units that we use. So we do not use exactly this term, since 1325 is not going to be a big change. We round it off to 100,000 pascals. As far as temperature is concerned, we measure temperature for gases in Kelvin, since Kelvin is the standard unit. So if we talk about Kelvin in Celsius temperature, it's Celsius plus 273. So 100 degrees centigrade is actually 373 Kelvin. Why is that so? We're going to consider that too in this book. Don't worry. Make sense?
Yes, sir.
Okay. These are some childish conversion questions. A minute will easily clear them out. So that actually gets you ready for the difficult past paper questions. Moving on. The pressure of a gas is due to collisions between the gas molecules in the wall of the container. Let's understand this point as a whole. Okay, let's make a diagram and let's consider that we have enclosed a gas in a system, a cylinder, and there are a few particles. So when I use the word pressure, what I'm actually trying to say is that I'm going to sum up all the collisions of gas molecules which they are doing between one another and with the wall of a container. A gas molecule hitting a wall of a container is same like a young boy playing with a ball against the wall. He's throwing the ball on the wall. The ball goes, strikes the wall, comes right back, and the ball has a specific area which strikes on the wall. Let's say that area, let's do it like this, is this one. So the ball comes with an exact force, strikes a specific area. Pressure is force over area. When we are taking it for a gas, we're actually talking about all the collisions between the gas molecules and the walls. Maybe sometimes if there is a separate lid, then we're going to include the lid and in between the particles. All of these are averaged and we call it the term pressure. So gases in a container exert a pressure. Since they keep on moving randomly, and they keep on colliding between one another and between the walls of the container, right? If we decrease the volume of
Yes, sir.
gas at a constant pressure, the molecules are squashed, and this is going to be an important point, to closer together and hit the walls of the container more often. This diagram explains it very well. Now, notice the number of gas molecules remain the same, but here they have more space, so there would be less collisions. And here, when we increase the pressure, they would have less space and they would collide more often with one another and with walls of container. So when the pressure of the gas increases and the volume decreases, since this was the volume for this much, when we increase the pressure, the volume actually decreased. I hope you understand we're still considering volume mathematically, which for any container is going to be length multiplied by width multiplied by height. Since length
Yes.
and width are the same, but height is the thing that we have differentiated in these two figures. So, of course, smaller height, smaller volume, larger height, larger volume. Make sense?
Yes, sir.
Good, great. So, when we do it, we tend to plot a graph with 1 over pressure and volume, and it comes as a straight line. It gives us a proportional relationship. Since we're talking about 1 over pressure, we can safely say that volume is inversely proportional to pressure. And in order to get a directly proportional relationship, we use this and we use this as two axes of a graph. This is actually a law in chemistry. So in some other books, maybe you'll find the name of the scientist for the law. In our books, since we do not tend to fill the entire book with the names of the scientists, so we keep it easy. Without the name, we discuss the law. So don't worry if you come to see this name in notes or in reference books, since that's the exact name of the law. Now, keep in mind, this law is relating pressure with volume. And here, what is important and what we have said on the previous page, and then it's not written on this one except over here, is that we try to tend to make sure that the rest of the conditions which may affect the system are kept constant. In order to get this kind of result, the rest of the affecting factors are kept constant. So in order to get a
Yes.
straight line, the temperature has to be kept constant. Only then you would be easily be able to get a straight line for pressure volume versus, oh, sorry, the reciprocal of pressure versus volume graph. Make sense?
Yes,
Now,
sir.
what are the terms that we use in A levels? The figure captions are very important since sometimes they contain the pieces of information which are not given in the rest of the page. Now, as the gas volume of the gas decreases at constant temperature, its pressure increases, and that's due to the increased frequency of gas molecules hitting the wall of the container. Now you'd notice slowly he's getting towards more of the gas molecules hitting the wall of the container and less of the hits in between the gas molecules are hitting with one another. And you'll see the same thing in marking schemes. They tend to emphasize more about the gas molecules hitting the wall of the container as a part of the pressure. That's fine. You can simply write this one to get your marks. And you'll see the same thing in marking schemes. Now, for an ideal gas, a plot of volume of a gas against the pressure shows a proportional relationship. Remember, this is for an ideal gas. Real gases may not exactly show a straight line. Since what happens now, two things. In real gases, the volume of molecules is not negligible. In real gases, intermolecular forces of attraction and repulsion do exist when the molecules come a little bit closer. When they are far away from one another, we may be able to neglect that effect, but once they are a little bit closer to one another, the fact may not be neglectable. All right?
Yes, sir.
Even if it's not neglectable, what are we going to do with that fact? Let's discuss it a little later since that's not the portion we're doing next. Now, a couple of important things. Two variables are proportional if there is a constant ratio between them. Look at the figures for temperature and gas volumes in the tables below. You'd notice we have some continuous figures, right? Take a notice. This one doubles, doubles again, doubles, doubles again. So only then we'll be able to get a straight line. If first at this one, then we double it, then we double it. Like this. Make sense? We have graph like this.
Yes, sir.
Okay, good.
Yes.
Now, this is something different. This table is not talking about volume and pressure. This table is talking about volume and temperature, which brings us to a different point. Here, if you see the gas volume increasing, you would also notice the temperature to be increasing. So if you talk about this specific important part, you'd notice that we right now are talking about this kind of relationship. And of course, right?
Yes, sir.
Hence, we can safely say when the gas is heated at constant pressure, and I've mentioned this to make the sentence easier for you, its volume increases. This is because the particles move faster. And don't forget, I've already discussed this and hit the wall of a container with a greater force, not with a higher frequency, with a greater force. Now, these two things, higher frequency and a greater force, are different. Higher frequency means they are hitting in a larger number. If it was hitting twice earlier, it is hitting four times, maybe five times, maybe six times. But Hitting with a greater force means if it was hitting with a force of 10 newtons, it might now be hitting with a force of 15 newtons, with a force of 20 newtons, with a force of larger than 20 newtons. Get my point?
Yes, sir.
Frequency and force are two different things and are to be considered in the same way. If you're going to mix them, you're bound to make a mistake which will get your marks cut, both in MCQs as well as in theory. So, for the pressure to be constant, the molecules must get further apart. The volume of gas at a constant pressure is proportional to its temperature measured in Kelvin. And for this, we have a graph like this, right? Again, we're able to show it like this. Now, in order to show a diagram like this, since you might also have noticed in IGCSE, we had a similar diagram, smaller tails, larger tails. The temperature diagrams are always tailed in O levels and A levels books to give you an idea about the greater force having a difference with greater frequency of collision so that you don't mix them both. Even the diagrams at their simplest levels tend to be different. Okay. Not only that, please notice that this volume and this volume are different, right? And though these volumes are different, the pressure applied over here, let's suppose the pressure was 100 kilopascal, means room pressure. This was also 100 kilopascal. So actually performing this experiment at room pressure is a pretty easy way to keep the pressure same. You can say you have done it at a constant pressure since in your room the pressure won't change until unless you bring some sophisticated instrument to increase the pressure, right?
Yes, sir.
As the temperature increases, and I'm going through these lines now, as the temperature increases at constant pressure, you cannot forget the condition every time. This is important. So this is emphasized in the book every time they write the lines. They do note it every time. So make sure when you are answering a question in exams, you do not forget or ignore the conditions. Mention them, no matter in how small a way you need to mention them, right? You don't need to write the whole thing at the constant pressure. You can shorten it up and still mention it in exams. Now, the volume of gas increases, molecules hit the walls with increased force. For an ideal gas, the volume of gas is proportional to its Kelvin temperature, similar to what we have written above the diagram. An ideal gas will have a volume that varies exactly in proportion to its temperature and exactly in inverse proportion to its pressure. Ideal gas का volume temperature से directly or inversely proportional होगा pressure से, this stays the same. Now, let me tell you something which you might not have thought, since we have a normal person's mind and scientists' minds behave differently. This law will be considered as Charles' law, as per the name of the scientist, in some reference books, notes, or over the internet. Now, when this law came out back at the end of the 19th century, I guess it was 1800s and something, this immediately caused a huge thought and views among the scientists at that time, since a normal person doesn't think or doesn't take this graph, what the meaning should we take from the graph, and we simply think they're directly proportional. We don't think otherwise. Now let me tell you what scientists at that time thought. They thought if we're going to double the temperature, we can double the volume. If we multiply the temperature by 10 times, the volume will be multiplied by 10 times. If we divide the temperature from 10 times, the volume can be divided by 10 as well. So there can be a temperature as low where the volume can be brought down to zero, and we might be able to come up with a cold gun or a cold ray which instantly brings the temperature down and makes the person or the thing next to you disappear, vanish into thin air. That is how a scientist thinks from this kind of graph. So it stirred up in all newspapers and books of that time that we have a law, and from there on onwards, they were able to discuss the fact of ideal and real gases. Before that, this fact was a thought, but it wasn't a stirred up conversation of the time. So it became the hot topic of scientists at that time, of that era. Imagine how a scientist thinks. They come to a
Yes.
conclusion that only hypothetical ideal gases are going to behave it, since no one was able to come up with a cold gun or a cold ray that, if fired on a person or a thing, makes it vanish into thin air. Yeah, they would freeze at that spot, like what usually happens in some cartoons and minions and stuff like that. A villain or a group comes up with a cold gun and instantly freezes anything in front of him. So yeah, we have a freeze gun. We may be able to come up with something like that in cartoons at least. But in actual life, that's not possible, since what we are dealing with is not ideal stuff, it's real stuff. We're not dealing with ideal gases, we're dealing with real gases. Now, $1 million question: if we're dealing with real gases, then why are we giving laws for ideal gases? The previous law was for ideal gas. This law is for ideal gas. Since we're not dealing with ideal gas, why are we giving even laws for them? Why are we giving laws for hypothetical stuff? Can you come up with an answer?
No.
Actually, for a human mind, working
Mm-hmm.
on hypothetical situations are much easier. उर्दू में कहानी होती है शेख चिली. A person who thinks that he would become a millionaire in a shortest manner of time by doing this, this, and this. Many people do that in actual life. हम में से बहुत सारे ऐसे होते हैं लोग जो कि hypothetical situation सोच के बड़ा खुश हो जाते हैं. If I'll do this, I'll invest this kind of money over there, and overnight I will earn back this much amount of money, and boom, I'll become a millionaire overnight. I'll become a billionaire overnight. But in reality, that does not happen. Even for billionaires, they have years or months of uh, underrated hard work. Actually, they have worked harder. Their hard work is usually underrated for the world, and the world still thinks about some hypothetical situation. People going to casinos and that those kinds of stuff, thinking about to coming up with a deal and may win, or there are jackpots, there are lotteries, that there are a lot of stuff like that. So we love to think about hypothetical situation. But does that help science? Usually, you may think no, but let me tell you, ideal gas or their rules are easier to develop, and from there on onwards, we can make changes to suit them to the real gases we're facing today. That's why discussing hypothetical stuff is important, since you can easily come up for an equation for hypothetical stuff, and then you can readjust the equation according to the real situation that you have. ठीक है. हाइपोथेटिकली एक
जी.
बच्चा ये सोचता है कि मैं ए स्टार ले लूंगा. रियल सिचुएशन में उस ए स्टार के लिए वो अपने डेज के आवर्स टाइम टेबल्स डिवाइड करता है एंड कम अप्स विद अ प्रॉपर हार्ड वर्किंग प्लान टू गेट टू दैट ग्रेड. आपने आईजीसीएसई में स्टार दिया है. You know yourselves, it wasn't easy. You didn't do it with movies and dramas and binge watching stuff. It took a lot of hard work, right? Keeping the
Yes,
geniuses
sir.
apart, there are some people who can make stuff true with least of the hard work. But of course, every type exists. But for most of the people, it's hard work. At least for me, it was. Okay, so coming back to this point, what I wanted to do was to bring a little bit of curiosity, which is going to make the understanding of the hypothetical portion of this chapter and the real portion of this chapter, since we're going to study both, easier for you. All right. So limitations of the ideal gas law. Scientists, if they can accurate measurements to show how the volume of gases change with temperature and pressure, this shows that gas do not always behave exactly as we expect an ideal gas to behave. This is because real gases do not always obey the kinetic theory in two ways. Number one, they are not zero attractions between the molecules. We cannot ignore them. And simply, we cannot ignore the volume of the molecules themselves. These differences are especially notable at high pressures and low temperatures. What happens at high pressures or low temperatures where we cannot neglect them? Now, let's think about it. At high pressure, the molecules will be brought closer to each other. Of course, they can show a little bit of attraction between one another. Since if there weren't any high pressure conditions, the molecules would be far apart and will not be showing any attraction. Make sense?
Yes, sir.
Lower temperatures tend to affect the kinetic energy of the molecules, and lower the temperature, slower would be the movement of molecules. Slower would be the movement of molecules, more bit would be the time for attracting forces of attraction between one another. Okay? Volume of
Yes.
molecules is not negligible as compared to the volume of container. Okay? And this thing under normal conditions, container and volume of molecules is negligible. But what if we have increased the pressure or decreased the temperature and now the volume of container is different? ये हिस्सा नहीं है, सिर्फ इतना सा part है. Now it may not be negligible, right? So at high pressure or at low temperature, these 2 points may not act the way they are written. So at high pressure and low temperature, IDID forces or PDPD forces becomes dominant and viewable. You cannot neglect them anymore. Attractive forces pull the molecules towards each other and away from the walls of the container, so they do not exactly uh, able to hit with that frequency or with that force. Actually, both. The pressure is lower than expected for an ideal gas, since if the frequency is less, the pressure would be less. The effective volume of the gas is smaller than expected for an ideal gas. This volume which would be effective over here is smaller than what is actually expected for an ideal gas. There is more explanation to this part, but if you understand these 2 points, you will be easily be able to understand the how the real gases behave. Remember, these are the two faulty points from the previous kinetic theory. These are the reasons for why these 4 points are faulty now. These are the conditions at which these 2 points become faulty, and these stuff starts to pair. This is the mathematical change that happens after all of this reasoning or these conditions have been met, and now these faulty points are converted into these ones. If there is zero traction, the pressure should be at its maximum. If there are attractions between the molecules, the pressure would be lower than expected, right? So the
Yes, sir.
pressure situation changes. Another case, the volume was ignorable between the molecules and the container. So at high pressures and lower temperatures, the effective volume is actually smaller than expected for an ideal gas. So the whole situation about the negligibility also changes. This phrase is still not as clear as the one on top. If you're thinking about the same thing, I agree with that. But let's move on a little forward, and this phrase would be more clear to you since studying the next parts will clarify the phrase. Am I right?
Yes, sir.
Okay, don't worry. If this is not clear and this one is more clear than the one at the bottom, we'll clear it up too. Okay, so general gas equation. What we do is that all the laws that we have studied, we actually put that into work, which is not shown over here. They quickly just tend to come up with the equation. I'm not going to do that. I'm going to explain it a little bit. Okay. The first law that we studied was like this. Understandable?
Yes, sir.
The second law that we studied was like this, right?
Mm-hmm.
There is another law which haven't been explained yet, but it's pretty easy to understand that these two also correlate. Now you're familiar that V stands for volume, P stands for pressure, T stands for absolute temperature measured in Kelvin and not in any other units. N stands for number of moles of a gas. N is the old unit that we used back in stoichiometry or moles chapter. So N is number of moles. So, of course, one mole will have less volume, two moles will have more volume, three moles will have more volume, so on and so forth. And you know about that molar volume or the value of for when n is equal to 1, the molar volume value is equal to 24 decimeter cube at room temperature and pressure, right? So if n is equal to 2, this becomes 48. For n is equal to 3, this becomes 72, so on and so forth. So we can, from these values, we can easily come up with this simple principle, right?
Yes, sir.
Make sense? If that makes sense,
Yes.
I'm gonna revert it. I'm gonna write it like this so that I can put V on the left and all of this on the right. Now let's combine all of them into one equation. Now in physics, we do not use the directly proportional sign and we tend to replace it with an equal to sign. Whenever we do that, we also add a, a multiplying constant factor towards the right hand side of the equation. This is something that we do in physics. So the same thing follows in chemistry. That constant is R. When we rearrange the whole thing, it becomes PV is equal to nRT. That's the ideal gas equation written over here. All right.
All right, sir. Okay.
No,
Yes.
now we are going to use small p, not capital P. I have been writing it, but let's go with the book since that's important. We do accordingly to the book. Small p, capital V, you know that's pressure of gas, that's volume of gas. T is absolute temperature. And remember, this is not normal temperature, this is absolute temperature, which means temperature calculated in kelvins and not in degree centigrade. Even if a question gives you a value of degree centigrade, convert it as the conversion factor given above, and we have recently studied. Now, what's left in between is R. You already know N is number of moles of gas and also mentioned over here. Now, in order to calculate N, it's pretty simple that we put it like this. For an ideal gas, we combine the laws, all these laws, and we come up with this equation. I've already told you how the combination occurs, so it's pretty simple how you get this part. Now, P is the pressure, and that is calculated in pascals. P is the volume, that is in cubic meters, like this. This is usually equal to this, or maybe equal to 10 raised to power 6 or a million cubic centimeter. You should be able to convert units. Number of moles of a gas is like this, and it's always over mass over mr, or it's not mr, it's mt. It is supposed to be mr, by the way. All right, maybe it's just a printing mistake. Now, R is known as gas constant. We also call it general gas constant from the word general gas equation. This is also known as ideal gas equation, so we also call it ideal gas constant. Since this equation is applicable to ideal gases so far, right? And this has a value of 8.31 joules per Kelvin per mole. How do we calculate it? Put in all the units for this. If you want to calculate R, how would you calculate it? You are supposed to calculate PV over NT. Now, if you're going to take it at a specific set of conditions, let's say standard conditions or room conditions, you can put all the values of pressure, volume, number of moles, and temperature for room conditions, and you'll get the value. So that's how we get this value. I hope that makes sense that N is at the bottom, so per mole, T
Yes.
is at the bottom, in Kelvin, and when you're going to multiply these two units, Pascal into this meter cube, you'll get the unit joules, right?
Yes.
Since that's explained in a work pressure volume principle in physics, that's usually not a part of chemistry, that is explained in physics. I guess that would be a part of your physics book when you reach the kinetic theory in physics, since that's taught in chemistry as well as in physics, both in O levels and in A levels. Temperature is next mentioned. Now, if we know any four of the five physical quantities in the general gas equation, we can always calculate the fifth one. That's pretty easy. Questions like this are considered to be the easiest questions and marks awarding questions. Let's see if you have four of these, even if the units are same, convert them, you know how to convert them, and get your answer for the fifth value. To change degree centigrade to Kelvin, you already know that a pressure of this many pascals is equal to 1 atmospheric pressure. I've already explained that. So worked example would be pretty easy to give you the idea how we can work around it. We're supposed to calculate volume, number of moles of gas, carbon dioxide are given, pressure of 150 kilopascal is also given, temperature of 19 degrees centigrade. You know the value of R. Convert the units into the correct units that you actually require. Put the equation, rearrange the equation, put the values, get your answer, and you can write your answer in the units that have been asked by the examiner or in the standard ones. It's entirely up to you. I think that's pretty easy to follow, right?
Yes, sir.
And I do not need to go into the nitty gritties or small portions of the solutions like step two or three separately. Am I right?
Yes.
Okay, good. Great. A flask of volume this much contains a specific mass of a gas. Now they are going to downgrade this equation to other formulas since he's not talking about the moles of a gas, he's giving mass. We want you to use the moles formula to convert it. And there you go, I was talking about MR and not MT, so that clarifies that was supposed to be MT. That was supposed to be MR and not MT. All right. So the temperature is given. Again, the temperature has to be converted into Kelvin, the volume units into meter cubes, and then the mass into number of moles. Only then we can put it up, rearrange the equation every time to what you're supposed to calculate, put in the values, and there you go, you have your answer. Now you can write the units in pascals, or you may write it in kilopascals. Uh, you can do accordingly. For example, if the pressure is given in kilopascals and volume in decimeter cube, you can insert these figures directly into the equation without converting them. This is because changing kilopascal into pascal, you're multiplying by 1,000, and by changing decimeter to meter cube, you're actually dividing by 1,000. So if you know this step, you do not waste your time into calculation, right?
Yes,
You
sir.
understand the point? So
Yes.
remembering stuff like this is a good point since it saves you time. Remember, if you substitute the pressure in kilopascal in the equation this, the volume of the gas will be calculated in decimeter cube. If you substitute the Pascal in the equation, the volume of the gas is to be calculated in meter cube. Since the units are in kilojoules, we need to balance them with both the numbers. If the volumes unit is greater, the pressure unit has to be smaller, or if the pressure unit is greater, the volume unit has to be smaller. This is a very important point. Students sometimes tend to forget it, and what they wind up with is that they either have multiplied the whole thing with 1,000 additionally, or they have divided the whole thing with 1,000, which wasn't required in the first place. So this is an important point related to units. All right.
Yes, sir.
Next up is a whole